Well, thanks for coming. This is track B. Before we start, I would just like to let you know that we're actually recording all of this, and it will appear on YouTube in about a week. So if you're missing the talks, or if you have to step out, it's okay. You'll be able to see it later on the internet. Okay, so first talk up here. It's my pleasure to introduce Parviz, who's actually been working with Spark on Amazon for a while and making it actually work on EMR. And today he's going to tell us about how he's integrated it into the existing tool base over there. So please.
Thank you, guys. Thanks, Ellie. Nice to meet everyone. First Spark Summit. It's super exciting, super exciting. So title, Making Spark Fly. And no, we're not going to do it with drones. The guys, whoever watched 60 Minutes last night, we're not going to do it like that. It's running Spark on Elastic MapReduce. So I've thought about this a long time. We had a reInvent session. I had to put content together for this session after that. And I had to thought about it a long time because the technical bar for this talk, it's high. For this conference, is really high. You've seen Mate talk. You've seen Ian talk. You've seen a bunch of people talk. I don't know if you've been to AMP Labs or AMP Camps sessions. The talks are super technical. So had to think about it a little bit more to figure out what I want to talk about. And I settled on the fact that the obsession that we have in Amazon, which is making things scalable, highly available, secure, and also left that out, which is make it efficient, cost efficient, but that comes without saying. So settled on that. So I want to talk to you guys on how to make Spark scalable and highly available. Don't have time much to talk about how to make it secure, so hopefully for next user conference. Anyway, so how do we make Spark scalable and highly available? We've done it with Elastic MapReduce. There are two approaches we could have taken here. We could have write a complete different cluster manager to manage Spark as a cluster and run that in scale on Amazon and Amazon Web Services. But we have Elastic MapReduce, Amazon Elastic MapReduce. And for those of you who may not be familiar with EMR, I'm going to give you a bit of an introduction. It's a Hadoop as a service, and I'll come back to that and what that means. But also it's a MapReduce engine which massively scales and massively parallel. And also very cost-effective AWS wrapper on top of a cluster of Hadoop. And it integrates with a bunch of tools that we have, and I'll go through that very soon. But it integrates with almost everything we have. So Redshift, EC2, with DynamoDB, S3, and every other product that we have. But let me come back to Hadoop as a service. There are two ways of running stuff. For example, you can be completely managed, meaning that you give us the application and we run that for you. But that's not how EMR is. EMR is a Hadoop as a service, but you have full control and flexibility on what do you want to do with that service. For example, you run the EC2 nodes, you have full root access, and you have a concept of bootstrapping, which I'm going to get into very soon. But we manage running and deploying Hadoop by itself, but you have fully control and flexibility as to what you want to run on those nodes, and I'll get into it. So again, a little bit of introduction. Amazon EMR, Elastic MapReduce, Hadoop as a service, comes with HDFS and MapReduce on top of it. Integrates with S3, Amazon S3, DynamoDB. Also, we have a bunch of platforms on top of it. Edgebase, MapReduce, MapR runs on it, Flume. Forgot to put it here, Amazon Kinesis also on top of it. Hive, Mahout, Pig, and you can run Scoop to move data from Hadoop to any relational databases such as RDS, MySQL, Oracle, anything else. And we've introduced Amazon Data Pipeline for you to be able to coordinate where data is and where it has to go. So if you have to move data from EMR to DynamoDB, from DynamoDB to S3, and from that to Redshift, you can do that with Data Pipeline. So finally, we introduced Spark, which runs on Elastic MapReduce right now. And you can take advantage of that. So I want to leave that slide for a bit so you guys can see, and you can see the whole ecosystem now being able to run on AWS, on EMR. So you have Spark running, you have Mahout running, you have Hive and Pig, you have Flume and Edgebase, almost anything within the same cluster running. So if you've taken advantage of all these services, all that is contained within the same cluster. Interesting. I promised you I had something here. I'm not sure where you're going. All right, so one, you're looking at the DOS. The first dot is a master node. So there are a few concepts I want to talk about. Master node, the second dot should be core nodes, and the third dot should be task nodes. So these are different concepts on EMR. So this slide is a little bit has missing information. So let me go to the next one. Let me introduce the concept of core nodes. Core nodes are just the simple Hadoop nodes. They run data nodes as HDFS nodes, so they have HDFS persistent storage behind the scene. The good thing about core nodes on EMR is that you can add nodes. So the concept of being elastic, meaning that you can add nodes if you need more data. If you need more CPU, if you need more memory, if you need more HDFS nodes. So it's a very simple concept. You call an API on our side, you go to console, you add more core nodes, all of a sudden you get more CPU, more memory, and more HDFS. The caveat with that is that because you're running HDFS, you can't remove these nodes. We could have made it happen, but what if you want to remove 2 nodes or 3 nodes? And if you remove more than your replication factor, you have the potential of having corrupted data. So we decided to not give you the ability to remove nodes if they're running HDFS. So again, you can scale them up, but you can't scale down. The second concept is task nodes. Task nodes are a little bit different from a traditional Hadoop nodes that you run, which has both data node and task trackers. Task nodes have task trackers only. They don't have data node, meaning that they don't run HDFS. So if you need to pull any data, either from S3 or from HDFS, you have to go over the network to core nodes for HDFS or over the network to S3 to pull data and do the processing. And again, the core concept here is that you can add CPU and more memory, but not HDFS. So if you need more CPU and more memory, just add more task nodes. But the good thing is you can add task nodes. You can also remove them. So you don't have HDFS. You don't have to worry about corruption on HDFS. So as many times as you want, you can add and remove them. So very elastic. So for the rest of this talk, I'm going to refer back to task nodes because this is where Spark comes in and where Spark shines, because you can add Spark nodes and you can remove them when you need to. So let's get into the meat of it. But before that, let me talk on how we added Spark to Elastic MapReduce. The technique or one of the features that we use to run Spark on EMR is bootstrapping. I'm a big fan of bootstrapping, so let me give you a little more details on bootstrapping. Bootstrap Actions on EMR is a way for you to install or run anything you want on EMR nodes. And when I say anything, I pretty much mean anything. The way it works is that you write a bash script, and bash script can be running apt-get. It can be running any Perl or any Perl programming, PHP, Java, anything you want, Scala. Write that in a bash script, put that on S3, and refer to that location of S3 for that bootstrap action when you run the EMR cluster. When you do that, we'll pull that bootstrap action from S3. We'll execute it on every node at the boot time. So if you're installing anything or if you want to download anything from third-party resources or tools, we can do that for you. So bootstrap action gets executed at the boot time, software gets installed, and you're good to go. And another good thing is we talked about being elastic. I talked about adding and removing nodes. The bootstrap action gets executed every time you add and remove nodes. So you don't have to worry about later on if you're adding nodes or removing nodes, how this bootstrap action is going to get executed. It will happen automatically for you every time. All right, guys, I'm not sure what's going on here. I promise you there's something here. All right. Whew. All right, so Bootstrap Actions. So with Bootstrap Actions, we're installing Spark on top of EMR. So currently today, it's Spark 0.7.3. I'm working hard to upgrade that to Spark 8. And this, the link below, it's a short link below, gives you the tutorial that I've written gives you exact steps of what you need to do to run Spark on EMR. But it's very simple. It's just one line command line, or you can do it through console. We'll give you the Bootstrap action URL, put that in EMR console or CLI, and execute that, and it will get installed on top of EMR. So why do you want to do that with EMR? Why do you want to run Spark on EMR? And one of the great use cases for that is if you want to get a Spark cluster up and running in no time. I literally kid you not, running Spark on EMR takes about 2 or 3 minutes for a smaller cluster. You want to go in larger clusters, maybe 100, 200 nodes. It probably takes you 5 to 10 minutes, 10 minutes at max if something happens and we have to replace nodes if nodes fails. But at max, you're talking about an average time of between 2 to 4, maybe 5 minutes to run a cluster on EMR, on a Spark cluster on EMR. The other great thing about it is that we take care of failures. For example, if something happens to one of the nodes, you're running 100 nodes. Statistically, there's a chance of failure happening. If something happens to that node, disk failures, any failure, we'll replace that node for you automatically. You don't have to do anything with that. We'll automatically replace it. And like I mentioned, we have integration with a bunch of other services. For example, Redshift, Data Pipeline, and Cloudwatch. But by far the most exciting one is EC2 spot market integration. So let me get into that. Oh, actually, one more thing. I've added, and this is going to come up with the Spark 08 on EMR that I'm introducing very soon, which is the ability for you guys to ship the logs to S3. We do already do that with Hadoop. What that means is that if you're running Hadoop, your task nodes, your data nodes, your task trackers, job tracker, all of them ship logs automatically to S3. So when you launch an EMR cluster, you say, here's my bucket. We automatically ship all the logs to S3 for later on processing. I've added that ability to Spark, and especially Spark Bootstrap Action, where you now can see your logs getting shipped automatically to S3 for better debugging and troubleshooting later on. So I talked about a little bit on EC2 spot market, which is ability for you guys to come in and bid on unused EC2 AWS capacity. So let's just say we have thousands of M1 extra large nodes laying around. 200 of them are being used. There's 800 of them not being used. We give the ability for you to come in and bid on those EC2 instances at the very reduced cost. We're talking about 80 to 70% cost reduction. So one of the great use cases for that, and we all know Spark is very memory hungry. For you to cache all your data set in memory, you need a ton of memory. So one of the great use cases of that, while running Spark on EMR, is leveraging Spot to get memory, as much as memory as you need. Here's a calculation I've done, and it just makes me excited. If you need 1 terabyte of memory, that's a huge cluster. That's a lot of in-memory data processing that you want to do. You have the option of going with M1 extra large, 63 nodes, amount of memory that M1 extra large provides. That means that you need 63 nodes. That's about $30 per hour of if you have to run that on demand or on-demand pricing model. If you come in and bid on EC2 spot market, that's about $4.41 an hour. That's a huge reduction for you guys. And I've done a calculation. That's about 44 cents per gigabytes per hour. That's cheap of memory. Same thing on CC2. Great use case for Spark. If you're memory heavy and if you're CPU heavy, CC2s are great for that. 16 instances, about $39 an hour. On spot market, that would be $4.46, about 46 cents per gigabytes of memory per hour. M2 quadruple extra large is even cheaper, $2.25 per hour, 22 cents per gigabyte. And typically, if you're memory heavy, you may use M2 quadruple extra large as well. But if you have the means to pay for CC2, you get a much better CPU power. So for serialization in Spark, and also shuffle, and also doing in-cache memory with Spark, CC2s are great. You still can do it with M2 quadruple extra large, but CC2s are great nodes for that. Didn't put it in here, but HS1 instances, these are huge boxes with almost 48 terabytes of spindles attached. Great use case for HDFS. I've found it being very performant with Spark. So if you're doing very disk IO intensive workload, HS1s are great use for that. EMR supports that node. and also has about 112 gigabytes of memory. And HS1, the one that comes with SSD, something I haven't played with yet, but it would be really cool to come up with a use case where you're caching your content, your data set in Spark, but also spilling to disk, but in this case it's going to be SSD, so spilling to disk is going to be much faster. Haven't done much performance tuning or testing on that yet, but in theory it's a nice concept. So here's a design pattern that we can go with. So let me go through this. This design pattern is going to assume that you're going to launch with this initial set of cluster capacity. Let's just say core nodes. Very small cluster, 32 gigabytes of memory, and also HDFS workspace. You store your data on HDFS. Now you need to run a processing or data processing workload. You go in and bid in EC2 spot market, the one that we talked about, and get nodes with enough memory, in this case 256 gigabytes of memory, for in-memory processing. Bid on EC2 market, you get that in your cluster. So now what you could do is you could load data using text file function on a Spark context, and also sequence file you can read directly either from S3 or directly from HDFS. Load up your cluster completely and run a computation on your RDDs, all in memory. Once you're done, what you could do is you can save everything, pretty much checkpointing your data. Save everything, persist data to HDFS nodes, which is the initial cluster that we ran, or save it back to S3. And you can run the functions on RDD, save as sequence file or save as object file. It will directly write to HDFS or S3. And what you could do is, now that your data is persisted, get rid of the extra capacity that you don't need. And the way you can do that is why the topic or the concept that I talked about, which was task nodes. You can't do that with HDFS nodes. You probably can't do that easily on EC2 either. So this is a great use case for EMR where you can add as much as memory you need, do whatever you want to do computations with RDDs in memory, and then save your result back to HDFS or S3. Get rid of the cluster and don't pay for what you're not using. All right, so I talked about initial cluster coming up and then expanding the cluster. So this was the initial cluster. You want to expand that to multiple nodes, as many as you want. In this case, 256 gigabytes of memory. But interesting, but how do you automate that? How do you make that easier for yourself? So you either do that through either maybe alerts, or maybe do that completely automated. And the way you want to typically do that, and I call this Autoscaling Spark in my next, actually in my first slide deck. Autoscaling Spark, and autoscaling is a concept on EC2 that we do almost on a daily basis, which is you get a EC2 node, CPU goes up, memory usage goes up, you keep adding and adding to that cluster or to the number of nodes to handle your data processing pretty much on demand. But how do you do that for Spark? And the way you do that is you find metrics, the metrics that you want to scale on. And the metrics you want to use typically depends on your workload. So you're either CPU intensive, you're either memory intensive. For Spark jobs, you're probably both. You're probably looking at a CPU intensive workload because of the serializations, and also memory hungry because of caching all the RDDs. So I want to give you guys a way to auto-scale that, but before that, let me get into the concept of Cloudwatch metrics. Cloudwatch, for those of you who are not familiar with Cloudwatch, is a way for you to monitor your AWS resources, so EC2, Dynamo, S3, Redshift, anything you can you like to monitor, you can do that with Cloudwatch. EMR comes with Cloudwatch integration, meaning that you can get metrics such as the load on the cluster. So how loaded is your cluster? How much HDFS are you using or maybe not using? S3 metrics, how much bandwidth are you doing between S3 and your nodes? So you get those metrics, something similar to this, automatically with integration of EMR. So what you could do with this CloudWatch metrics is a way for you to get alerted if you have something that you've set up as a breach of a threshold. For example, let's just say you want to get alerted on a CPU utilization of your cluster. You can set that up with CloudWatch. Set up a breach point in CloudWatch, say anything more than 50, 60 CPU utilization, alert me. The alert goes through SNS notification. Now, SNS notifications can be both in email, actually 3 ways. Can be email, can be SNS to your, SMS to your cell phone, or also can be HTTP API calls. And HTTP API calls is a way for us to let you know on an HTTP endpoint if something happened. So it doesn't have to be email. We can just ping you at an endpoint, let's just say API-foo.com, and give you enough information as to when that alert was breached. And what you could do with that is CloudWatch metric, get an SNS notification, my metric has breached, receive an email notification, take some sort of automated action. So in the context of Spark, what you could do is you can set this up on a total load metric on EMR, get an SNS notification. Let's just say you're doing some sort of Spark processing, CPU utilization goes high, get that notification. Once you get that notification, go add more nodes to your cluster. So this is based just completely, you can automate this, but for now, it's either email or SMS. But what if you want to do that with memory? We've talked about CPU. How do you do that with memory? And a typo there, should be lots, not lost, but lots of it. So how do you do that with memory? Spark 0.8 introduced something really great, which is Spark metrics. It's a concept of sync, source and sync, meaning that source collecting data, sync pretty much gathering data. So if I've introduced, sources here, you would have workers as sources, drivers as your source data sources, and also executors as your sources. And you can collect JVM metrics. The syncs would be console syncs. So if you have a console for Spark, you get that on your console. You have JMX, you have CSV, you can get everything in CSV, and also Ganglia sync. So you can see that in Ganglia. So if I've written some sync for CloudWatch sync. So now what you can do is you can have Spark cluster running on EMR and publishing the metrics to CloudWatch. And the reason, I'll give you sort of a snippet of it. This is how it's going to look like. For example, if you have workers that will introduce something like JVM hips used, JVM hips unused, or how many executors you're running, how many workers you're running. You can monitor all that with CloudWatch with the Spark 0.8 on EMR. And what you could do with this, the good thing with this is that you can set up alerts and breach points on your CloudWatch metrics. So for example, if you're using more than 20 gigabytes of JVM used, what you can do is you can get automated SNS notification, HTTP SNS notifications, and you can automatically start adding nodes to your cluster so you don't get that JVM OM out of memory error. And if you've worked with Spark, that comes up a lot. And probably running short on time a little bit, but so I've also worked on integration with Amazon Kinesis. To give you a little bit of introduction on Kinesis, if you're not familiar with it yet, it's something we launched at reInvent about 2 or 3 weeks ago. It's almost a Kafka as a managed service. So if you're ingesting a ton of data, you're doing that with Kafka today, Kinesis will do that for you as a managed service. And a very simple concept, producers will write to shards. Shards are, each shard can scale up to 2 megabytes write and 1 megabyte read. And you have consumers, workers reading from Kinesis. Now, API, very similar to Kafka. You can create streams, you can put records, you can get records, you can create shards. We have a concept of creating shards and also merging shards. So if you have a shard that is doing more than what it's supposed to do, like 1 megabyte read or 2 megabyte write, you can split that to multiple shards so you can scale based on that, and you can also merge them together if you're not using them. Spark on EMR, Spark streaming supports Kinesis. So in this case, we're putting workers on Spark the implementation on EMR. Each worker is a consumer of Kinesis. We'll go to Kinesis, read the records, and process them. So again, it's a new Spark streaming Kinesis receiver. Should be up on a Spark 0.8 soon, as soon as I put them up there. Extends network receiver. If you've worked with Spark streaming, is one of the interfaces that it supports. And again, creates a single receiver worker per shard. So if you have multiple shards, we'll create multiple workers, all pulling from Kinesis in parallel, do the processing, all in parallel. Just give you one more miscellaneous section for you guys. Doesn't relate to EMR. Doesn't have to relate to EMR. It has. You can do this without EMR. We've introduced new instance types called C3 instances and I2 instances today. C3 is out already. They provide a much higher packet per second and also much better CPU power, but also gives you much less network jitter, which what that means is that you can run high packet per second nodes with high packet per second load, and you won't have noisy neighbors. Great use case for Spark, especially for serialization and also doing shuffle speed between nodes. I haven't tested it completely, but I've seen a great stuff from initial testing I've done. And last, I'm really excited to working on more stuff on Spark. If you have ideas, if you have things that you like to see on Spark, especially on EMR, definitely let me know. I'll be around. Give me ideas. I'll definitely be happy to work on that. So thank you.
So any questions for Parviz? We can probably take one. Yeah, you please stand up. They might film this.
What would be the advantage of having the HDFS there? Why wouldn't you just go straight to S3? So why did you go with a straight elastic compute cluster?
Yeah, very good question. One thing that HDFS may, going to S3 may not be really good for is for iterative workloads, especially everyone here probably aware of that. Machine learning stuff. So if you're passing through your data multiple times, processing data multiple times, going over the network to S3 is not efficient. So what you want to do is you want to copy that from S3 to your local HDFS and run your multiple passes over the data on HDFS on local nodes. But we have a ton of use cases that they never touch HDFS. They go to S3, for example, Hive is a great use case. They go through S3, pull from S3 directly, we'll do processing, or in this case, we'll do caching and RDDs. We'll do a lot of processing right back to S3 directly or right back to HDFS. But yeah, really good question.
Okay, thank you. All right, so yeah.